still was having license issue. But she is saying it is not sorted out. Oh, but okay, you have the latest information. Okay, that's good. Good to know. So I can try it out. Let's see. I mean, if I have time after this, I'll just try. Or I can basically say, live show them that it's not working. And then screenshots. Okay, so any questions? No? Okay, so let's continue with whatever we were saying. So at the end of the last class, I kind of finished it off in a hurry. There were some questions on how to find out those h of k's, right? So in principle, what we are doing is this. If you have an input, it was j omega naught t. If it's an LPDV system, so you can break it up into these sideband, these different paths. And you multiply each path with its corresponding harmonic number, right? This is j omega st, minus j omega st. Here, obviously, multiplied by it was 0, so it doesn't make any difference. And you add them up. So this is nothing but summation of hk j omega naught. So this omega naught is the same as this omega naught times e to the power j k omega st, summation of all k times e power j omega naught t. Right. So basically, this is a ZA expansion. So it's called. The ZA expansion of LPTV systems. Now, what did we do earlier? We essentially said that we were trying to find out each of these harmonic sidebands. So now, what we need to be mindful is that these are all functions of omega naught. I don't know why that thing came again. Okay, so these are all multiples of omega naught or omega, whatever be the input frequency. So then the question arose is that experimentally, I mean, now this is a model, right? Model of a system. And the system that we had was, in our case, was this. So we were taking the voltage across the capacitor in one case. I'll now call it VLP because we know it will be a low pass response. Another case we were taking here, I'll call this VBP because we know that it will kind of have a band pass response also, right? So depending upon where you are taking, you can have your output to be, this will be summation of VLP j omega naught e to the j omega naught t times e power j k omega s plus omega naught t. Or if you take it from here, this will be summation of h bp j omega naught j k omega s plus omega naught t. Summation of all k. Okay. So the way we were going about doing it was, we essentially said that we are observing VLP at the falling edge of the clock, and then we, under the assumption that RC time constant is much greater than TS and so on, we could figure out that this is equivalent to saying whatever, what it is equivalent to saying that the voltage across the capacitor is essentially the average of the on time of the signal, right? And because RC time constant is much, much larger than this on time and all, this whatever voltage across the capacitor we are sampling, that persists throughout the cycle, right? Depending on off time, definitely it is going to persist. There is no leakage. In the on time also, there is no significant change on the value of the envelope, right? So I mean, using those perspectives, we could figure out, we essentially could figure out that this guy effectively reduces to summation over k HLP j omega naught times e power j k omega s plus omega naught times t on. Right? It is equivalent. It is sufficient to find. It is sufficient to find the envelope at t on. If I find the envelope of t on, we are postulating that throughout the cycle, that envelope does not change. Right? So it is at one time instant we found out, and based on that, we made all the other derivations, right? If you have to be really, we also saw how to go about doing the brute force analysis for any t, for any RC time constant. But after we did the entire thing, we are moving towards the scenario where RC time constant is much, much larger than the on time. And hence we said that we can replace this t with t on, provided this, I mean, and assume that it does not change over the cycle, right? So that assumption it will be valid as long as RC time constant is much, much greater than 1. And under this assumption, we could also figure that if that is the case, the voltage across this VLP, or voltage across the capacitor, will only have low pass response. It will not have any high pass response. And how did we figure it out? We obviously, the averaging gives you an idea, right? If you have higher and higher frequencies, and if you average, the capacitor will see more and more. I mean, capacitor is going to see not only one particular, the capacitor is not going to see the same portion of the sine wave every cycle. It is going to see a different portion of the cycle every cycle. Again, I had asked you to do an example of it if omega is not equal to omega s, right? So if you do that, then you are going to see that there is, because of this effect, there will be some attenuation. There will be some attenuation of the signal, and as you go higher and higher frequencies, that attenuation will become larger and larger, and there will be, I mean, just like any frequency dependent network, you are going to find out a particular value of omega for which the frequency response drops to 3 dB of the maxima. That will be the bandwidth, and so on, right? So we did the bandwidth thing in a brute force method, and I asked you to figure out whether it's the same thing if you do this averaging thing also. Now, where the class ended yesterday, the day before yesterday, was let's say we have a network which I was able to decompose into this ZA expansion. How do I go about finding out this H naught, H1, H minus 1, or Hn or something, right? So what does this mean? So now if I have to find out, let's say H naught j omega, so, or rather, let me just make it generic. If I have to find out Hk j omega naught, right? So we have to be careful with what these notations mean. So this notation means that input has been applied at omega naught, right? So input is, I could simply say input equal to e power j omega naught t, right? I am looking at the kth sideband at output, because input obviously does not have any sidebands, right? I'm looking at the kth sideband at the output. So which means that your output will have a frequency of omega naught plus k omega s, right? So output is, I am basically looking at the coefficient of e to the power j k omega s plus omega naught t. So whatever is this coefficient is this, right? So if I understand this, then from the ZA expansion, it should be sufficient that we need a framework to take out only one of these paths. So let's say this is the hk j omega naught. This is getting multiplied by e to the power j k omega st. And you have access to only the output. You only have access to here, right? So this is a box. You don't have access to inside this box. You only have access to terminals. So what type of experiment would you run to find out experimentally what is the value of hkj omega naught? Or rather, how would you modify your this entire setup? This, assume this is the device under test, right? So this is called DUT, device under test, which is a Swiss Starseed network or whatever. It's an LPDB network. You have access to input and you have the access to the output. How are you going to find out hk of j omega naught? I want the output to be only comprising of hk j omega naught. Multiplied by something is okay, but no other sideband should come. So what should I do?
So do you know what omega s is?
Yes, you know omega s. Because generally omega s is something that you are controlling from outside only, right? So you know omega s. So what are you going to do? So in general, let's say you have to run an experiment in the lab in an LTI system. You have to find out the transfer function. What are you going to do? It is another midsem question. So let's say you have now access to signal generators. So what are you going to do? Huh? You are going to give a sign, and then let's say you give a sign at a particular frequency, and at the output, what are you going to see? You are going to you're putting a spectrum analyzer. You are going to see something, right? What are you going to see? Why multiple frequency? LTI system. Yeah. Impulse at the same frequency at which you have given the input, correct? And anywhere else, you are not going to see anything other than you probably will see noise, but experimentally, you will never get rid of noise. You're going to see noise, but you are going to see an impulse at the input. So now if you have to take when you have that input, so that is, you put it there in a spectrum analyzer and you are looking for that impulse and you are finding out the value. Experimentally, what does it mean? You are putting a band pass filter around the frequency of interest, and the power at the output of the band pass filter is conveying the strength of the transfer function, correct? So the key thing to take away is that we need to put a band pass filter around the frequency at which I'm interested which I'm interested in, correct? So now here I have LPDB system. I know that I'm going to get all bunch of sorts of impulses, but I am interested in finding out hk of j omega naught. So where would I put that bandpass filter? So essentially, I still need a bandpass filter. We agree? So I need a bandpass filter here. And the output of the bandpass filter, I want it to be hk j omega naught e power j k omega st plus omega naught t. Correct? So where should I put the bandpass filter? Exactly, right? So that bandpass filter will be at k omega s plus omega naught. Right? So if I put the bandpass filter at k omega s plus omega naught, then I would be able to find out exactly the strength of the harmonic at which for which I am finding out hkg omega. Okay. So if we are now, let's say I want to, so this is if I want to find out hkj omega naught for uh, for any j omega naught e to the power j omega naught that I am applying. Okay. Now let's say I want to find out hk of, or rather I want to find out h1 of j omega s. This is what we were doing the day before yesterday. Where will you put that bandpass filter? Right. So this bandpass filter will be at 2 omega s. Right. In other words, in your in this system, let's say I want to find out HBP J omega naught, where omega naught is omega s, right? That is, I'm applying e to the power j omega st, correct? And I want to find out h1 of j omega s. What should I look for in the spectrum? I should look for that value of the tone that is appearing at 2 omega s, right? So that is what we were doing day before yesterday, right? If I ask you to find out what is HLP J omega s, right? And I want to find out the H1 of this, right? So HLP 1 J omega s, right? So by the way, I should have mentioned it should be I want to find out HBP 1 of j omega s, right? Because simply saying VBP j omega naught does not make any sense because it is going to have a whole bunch of stuff. I'm looking at one particular sideband. So similarly, I want to find out HLP1 j omega s. What will be the at the output? Where should I put the bandpass filter? 2 omega s, and approximately what are you going to get? You're going to get 0, right? Because the capacitor is going to filter out everything, and you will not going to get anything at 2 omega s, right? That we also saw using brute force method, right? You got notches at multiples of omega s, if you recall, because there was a zero order hold operation. Because of that zero order hold, you were getting notches at each of at multiples of omega s when observed across the capacitor, not on the other end of the switch. That's an important distinction to make, right? Your HBP1 j omega s will have a finite value, but your HLP1 j omega s will be absolute 0. Okay, so that is an important distinction So your HBP1 j omega s, will it be 0? It won't be 0. Everybody understands that? Intuitively, why will it not be 0? I am saying that HLP1 j omega s will be 0. So this will be 0. But this will not be 0. In fact, I am arguing that this will be very close to 1. Why? Or is the argument not valid? I did not complete this. So this also had this, right? So firstly, HBP1 j omega s is not equal to 0. I'm saying that HBP1 j omega s is not equal to 0. Is that do you have any doubts about that, or do you have? Because I'm seeing, I mean, some of you are nodding, some of you are confused.
We have seen mathematically it won't be zero.
Right.
But how intuitively we can.
Yes. So now that's the question. Intuitively, how do you know whether it will not be zero? Because this intuition is important, because I mean, when you are doing whole bunch of mathematics, you are going to arrive at some answer, because you are going to write some equations, you're going to solve it, some output will come. How do you know whether the output what you have got after a bunch of algebra is right or not? So you should be able to intuitively also argue that whether things are right or not. If you put pen to paper, you are going to get something. So how do you know whether you're right or wrong? So what is the relation between VLP and VVP? In time domain, how do you express VVP if you know VLP? Multiply with S of t, right? So you have multiplication in time domain, correct? Which means convolution in frequency domain. So if you have a DC value in time domain and you are convolving it with or rather multiplying it with S of t, what are you expecting in frequency domain? Right. So whatever you are having at DC is going to spread around, and it will get replicated at multiples of the switching frequency. Correct? So hence at 2 omega s, at omega s and 2 omega s, you are going to see non-zero outputs, because you are seeing non-zero outputs at DC across the capacitor. Does that make sense? Anway? HLP1 j omega s is 0. That's true. But what is non-zero? So, okay, now let me, since you have brought it up, let me ask you this thing. So which component, which sideband of at VLP j omega s will not be 0? Yeah. So if you have HLP minus 1 j omega s, this will not be 0, right? Because where am I seeing that? So this means that I'm observing at DC. At DC. Correct? So this is not 0. So this guy, this DC component gets multiplied by S of t. We did it last class also. That's why I'm not explicitly writing it out. I want you to think. Can you see it happening without me writing it down? Okay, so maybe let me spend a couple of minutes on this. So let's say we are saying that HLP minus 1 is not equal to 0. You're okay with that? Okay. So which means that with respect to time, I have flat line. Correct? And I'm multiplying this with S of t. And what is S of t? So what at the output after multiplication? So this is HLP minus 1 j omega s. Correct? So what do I get at the output? So here you are going to get a DC value, right? Correct? So this is the DC value, right? So I am trying to get VBP, right? So I'm trying to get VBP. So what do? I multiply with S of t. Correct? So if I multiply with S of t, VBP will essentially be scaled version of this S of t. And the scaling factor is HLP minus 1 times j omega s. Correct? So what will it have frequency component at omega s to omega s? There are two types of nodes. Okay. Yeah, I mean, different contexts. I mean, when you go to different parts of India, the nodes change. So it takes some time to understand whether this means yes or this means no. Okay, fine. So we agree with the fact that the 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 non-zero harmonics at the bandpass node is a result of the zeroth harmonic being finite at the low pass node, right? For this particular case, right? For this particular structure, this is not a universal truth for this particular structure, okay? And another key point to take away is that across the capacitor, approximately only the zeroth harmonic exists, everything else is zero, right? It almost behaves like a low pass filter with the RC time constant of NRC, right? Okay, so now does it make sense that where should I put the bandpass filter and what should I get using a ZA expansion? Okay. So now if I give you any LPDV system, you should be able to design an experiment to find out what this will be, right? So what will be that experiment? You find out you find out that at certain time instant, whichever time instant you are comfortable with, find out the transfer function, or rather find out that h of j omega that time instant. And if you can establish that that one persists, that does not change, then you fix that value, and then you see how it gets multiplied with something else, and then you kind of put bandpass filter wherever is necessary. If that is not possible, then it's not all circuits that will be possible, right? It's not necessary that every circuit has a very low pass node. So then you'll have to do brute force, right? Then you basically find out that ht of tau, find h j omega t, right? So once you find h j omega t, then for each value of t, you have to, each value of t is going to give you some h j omega, correct? And hence that thing you are going to expand into ZA approximation. And then from there you put bandpass filters and you find out, right? So that is a brute force method applicable for any LBDV system. Under certain constraints, you can reduce those brute force and work accordingly. Okay. Okay. So that being said, let me now move on to completing this circuit. So when I say completing the circuit, what I essentially mean is this. So if you have an LPDV system which is varying at omega s, and you have an input at equals j omega naught t, so naturally your output is hk j omega naught to the power j k omega s plus omega naught t. And this varying at omega s, this happens because there is some internal variation that you are giving, right? I mean, it's not happening by default. You have to use some clock or some sort of excitation that we are not counting it as an input because that is a fixed excitation. Just like you have a DC voltage source, you can assume this is another source which is affecting the system, right? So this is you can assume that maybe it's a clock or whatever, which is at s of t. Okay. And if I assume that I have not assume, let's assume, let's consider a situation where I have another the same, I replicated the same network, but this clock is time delayed with respect to the previous clock. Okay. And now I'm going to put a constraint. Assume that this delay is a fraction of the total time period of the clock. Okay. this delay. So if S of t has a time period of Ts, right? I assume that the bottom network has a clock which has a delay of Ts over n. Okay. Yeah, T on. Yeah, right. So in the example that we are doing, n equal to 4, right? And by the way, I have not in this is a generic case I am taking where I am not even assuming that S of t is a square wave. S of t can be any variation. Square wave is a particular case of LPTV, right? As long as S of t is periodic, LPTV is sustaining, right? So it can be weird shape, triangular, sinusoidal, something I do not know, but as long as it is periodic, the LPTV or relationships are valid, right? So but if it is periodic, then I know that it's periodic with certain interval, and that interval is Ts. The bottom clock I am delaying by Ts over n, where n is an integer. Okay, fine. So what am I going to get as output? So will hk j omega not change? How does this keep coming? I don't understand. To find this out. So what am I going to get at the output? So let me break this down, right? So what did we get here? Here I got it was j k omega st. This was multiplied by it was j omega naught t. Correct? Okay. So I delayed the clock. So where is that effect of time in the transfer function? Right. So the exponential has an effect of time. H of k does not have any effect of time. So when I delay the clock, so do you expect h of k, hk of j omega to change? No. Right. What do we expect it to change? The exponent we want it to change, right? We expect it to change. So basically, I mean, other way of thinking about it is that this is this is h j omega naught comma t, right? This t is going to change because now I am applying the variation is because of the t, and the period is, I mean, the phase of the variation has changed, right? So instead of this t, I am going to write t minus Ts by n. Correct? Because all this variation is happening because of the culprit is this S of t. Otherwise, this phase, I mean, this envelope wouldn't even have been a function of time. So whatever is happening with the t, or whatever is causing the variation, if I change that variation by certain instant, the envelope will also shift by the same amount of time, right? So that's all it is saying. So which essentially means that I can say this is hk j omega naught, this is j k omega s t minus Ts over n times it was j omega naught t. Okay. So if I just stare at this part, what is it saying? It is saying j k omega s t times e to the power minus j k omega s times ts is 2 pi over n, right? So this is this part. Okay. So if I let's say I keep doing this and I take n such copies. Okay. And I add up at the output. Whatever, after getting all these n copies, I add up at the output, right? What I essentially mean is this. So this is s of t minus Ts by n. I add up at the output. So what would I get? I would get essentially this summation of all these things, but this hk j omega naught and times e to the power j omega naught t will be common. The part that will only differ is e power j k omega s. This guy, right? This guy is the one only that will differ. So I can basically say that this is equal to summation of hk j omega naught j k omega st times e to the power j omega naught t plus 1 plus e to the power minus j k or e to the power minus j yeah
Yes.
k 2 pi by pardon yeah. So if n equal to 4, let's say, so if n equal to 4, then 2 pi by 4 plus u minus j k sorry no, no, yeah, so I think I messed up something. So I am so basically correct. So this becomes a to the power 2 pi by 4, then 2 pi by 4 times 2 plus u minus j 2 pi by 4 times 3, right? Yeah, k will be there. Correct. K will be there. So now for k equal to k equal to 0, right? Which means k equal to 0 means what? Which sideband? 0th sideband, which means the fundamental sideband, right? K equal to 0 means you apply input at omega naught, you are checking the output at omega naught, right? So for k equal to 0, you see that you can think of these as phasors, right? So one is this, then another is this, another is this, another is this, kind of, right? For k equal to 0, all these phasors line up. Correct? You get 1 plus 1 plus 1 plus 1. Correct? For k equal to 1, what do you see? Yeah, for k equal to 1, you essentially get this. So for k equal to 1, your output will go to 0. Similarly, for k equal to 2, 0. K equal to 3, 0. K equal to 4, again you are going to get 1 plus 1 plus 1 plus 1, right? So by doing all this addition, right? So what are you seeing? What is at the output? If this is a new LPTV system, still this entire thing is still an LPTV system varying at omega s, right? There is only one clock only. The clock is just that they are shifted with respect to each other. But the frequency, fundamental frequency of all the clocks are same. Do you agree? So I can say that this is a new LPTV system varying at omega s. Okay. And in this new LPTV system, the h of 0, right, of this new LPTV system is non-zero. H1 is 0, H2 is 0, H3 is 0, H4 is non-zero. So do you see a benefit of this type of LPTV system? Let me put a context. Assume that we are so when you had a switch to RC, right? The HBP, the bandpass response, was having something like this. So 0 omega s, 2 omega s, 3 omega s, and then we had 0 here and so on, right? Here, this is H0, correct? This was H0 of j omega s. But this guy was H1 of j omega s, which is non-zero, okay? So when you are doing bandpass filtering, right? and you want to do an LTI type bandpass filtering, let's say, then you would only want this guy to be there, right? You wouldn't want nearby peaks, isn't it? By adding up all those stuffs, what did I do? But yeah, correct. So by adding up all those stuffs, this here, what I let me just say h nu j omega naught comma t. So I saw that h okay, this is abuse of sigma because I'm using hk everywhere. So let's say I call it hk h new. Tell me some new name. Okay, h new k. Okay, so this is h new 1 j omega s. This becomes 0. Correct? Because these phasors cancel each other. So you get 0 here. Similarly, you get 0 here. But you get something here, right? But having said that, there is a lot of difference between, there's a lot of frequency difference between these where you have a 0 and where you have non-zero, which means that you can probably put a, the filtering of these higher sidebands becomes easier if the next sideband is at much higher frequency, right? So, so the good thing about having multiple phases, n becoming high, was we are having sharp filtering. But only having n equal to high was not sufficient because we were getting these additional nearby peaks, correct? But by putting n equal to high and replicating the same setup multiple times by just shifting it with respect to time and adding them up, we should be able to get rid of these sidebands also, right? And hence, it will make our life easier from a system level perspective if you want to bandpass filter. Make sense? Okay. Yes.
From the data,
Hmm.
had the model in which we had frequency, in which we represented everything in frequency domain.
Hmm.
And in this model, which you drew below,
Hmm.
where you take order T minus TS over alpha.
Hmm.
So this is the same thing, but in time domain, right?
No. This is not ZA, right? It looks like multiple branches. Doesn't mean all the multiple branches have the same meaning. This is nothing to do with that. This is a completely different thing.
What that why you started?
Okay, so assume this. So now let me put things together. So that probably will help. So this was one setup. S of t, SB of t, right? So here you are applying an input, e power j omega naught t, correct? All we are doing is saying, I'll copy this same setup, connect the same input, but just that instead of S of t, this will be ST minus TS by N. This will be ST minus SB of t minus TS by N. And then I'll go to and this will be ST minus N minus, T times N minus 1 by N. So SB T minus N minus N by N TS. Correct?
Without using an external bandpass filter.
Hold on. Let me just complete this. So all we are doing is that this is not sufficient, right? So if we observe this point, all we do is we took them up and add them up, and this is what we are taking. This is, if you do this, then you get this.
So without using any bandpass filter, we can find out what might be the sideband.
No, you are getting rid of this H1 of j omega s, right? That's not finding thing. You are actually getting rid of H1 j omega s, isn't it? Is that not clear? I mean, so after I drew this, hopefully this will probably become clear, right? So the previous part was theoretical. This is at least we have some circuits. Okay, so the, yes. Right, right. So essentially we are searching for a good bandpass filter, right? A good LTI bandpass filter will have a very sharp response, in-band response, or rather it should have a flat in-band response and a sharp roll-off, right? And nothing should come after that.
Here in this case, don't have sharp. That case also we can extract the property.
No. So okay. So let me finish his question, answering his question. So if I use only one single RC kernel, it's called a kind of a kernel. If I use a single RC kernel, we are going to get sidebands which are very close by, right? Which are not necessarily good for the applications. I mean, if we are ultimately everything we want in LTI, right? So if you are making a mobile phone or cell phone or anything, you want an input at a certain frequency, you want the output at a certain frequency, and nowhere else. Correct? So that nowhere else is important. So if you have peaks at multiple places, then that violates that condition of I do not have anything at anywhere else. Right? So the good thing about LPTV system is that you can make sharp filters. But the problem is because it is based on periodicity, you end up having things that are at some harmonic frequencies, right? So if we cannot get rid of harmonic frequencies totally, what we can at least do is to make them far apart, right? So having one kernel was making it like close by 1 omega is apart. Having 4 of them or n of them is making it appear after n omega is apart, right? So that's the motivation. Okay.
Now you can use any kind of bandpass filter.
It mimics a better bandpass filter. That's all it does. Right? It mimics a very sharp bandpass filter as long as the RC time constant is really large.
Actually using any external bandpass.
No, nothing. This is a bandpass filter.
Extracted omega.
Correct. Right? So, no, okay. So having, there's a caveat. So I'm assuming that if you have a bandpass filter, which is, for example, you add this up, and then you have to put a bandpass filter. But this bandpass filter need not be only around omega s. Right?
Even if it is not a sharp roll-off, then also we can extract the signal properly.
Yeah, exactly. Right. So you can have a lousy LTI bandpass filter upfront, right? But the job of that bandpass filter is not to differentiate between signals which are very close to omega s and omega s. The job of the that bandpass filter will be to differentiate between which is the harmonics of 4 harmonics or n harmonics of omega s and omega s, and that is a much easier thing to do, right? Yeah.
As a bandpass filter.
If we want to, because I have not explicitly talked about any application till now, if we want to use it as a bandpass filter, then this is a good proposition now, right? If the input is at omega s, we are getting. If the input is not at omega s, we are not getting any. That's all it means. Correct? There is a caveat. So if you, what this is essentially doing is if you have an input at, so let's say this is the part that you are tapping out, right? Wherever I have shown in the red color, you are tapping out. And ultimately, in any signal processing chain, you would like to digitize. After some time, you want to digitize. So before you digitize, you would like to ensure that you have a pristine signal without any other distortions available. Correct? When I say distortion in this I do not mean nonlinearity, but without anything else available. So in this case, if you do not have these 4 of them together, you have only one of them, and you observe the voltage only across the switch of one kernel, you are going to see tones at wherever you want at omega s, but you are also going to see tones at 2 omega s, 3 omega s. Can you tell them once? Today is Saturday's timetable. So, sorry, today is Monday's timetable. So you are going to see tones at omega s, 2 omega s, 3 omega s, right? And that, if you have to get rid of the tones at 2 omega s, 3 omega s, then you essentially need a bandpass filter. Correct? So the other way to think about it is that you want to put a sinusoid here, right? So you apply a sinusoid here, and you apply, and when you take this out, you would want this to be also a sinusoid, right? But if you have only one kernel, you are not going to have only one of the sinusoids. You are going to have sinusoids at twice, thrice, and the fourth one will not be there, and so then there will be, right? And you are going to get adding summation of these overlaps of scaled versions of these. But if you have 4 of them together or n of them together, you are not going to get this. This will not be there. This will not be there. The next thing that will be there will be n times higher frequency, right? Which means that I take this out and put a bandpass filter around omega s, and omega s, and this bandpass filter can be very lousy, like it can be maybe going to 0 around 4 omega s. That itself will be suffice. That itself will suffice. But if I only have one kernel, this lousy bandpass filter, LTI bandpass filter, has to go to 0 at 2 omega s. So that's the pitch. It does not say, by the way, nowhere I am saying that if you have an input at 2 omega s or 3 omegas, it is going to get filtered. We'll come to that. This, note that what did we do? This h of, where was it? Okay, so in this case, in the case of an RC time constant, this RC network, we said that HLP of j omega s is HLP 1 of j omega s is 0, HLP minus 1 of j omega is not equal to 0. This we said, right? So if we see, can we comment on, or rather, can you intuitively comment on what will be, let me write it here separately. By the way, this is a slightly different discussion. Okay, so let me put that caveat. I was planning to come to it later, but sorry, not here, right? So what will be h minus 2 j 2 omega s? HLP. Will it be 0 or will it be non-zero? It will be non-zero. It is observing at DC, right? And you are essentially, if you think about it, h minus 2 j of 2 means what? If you have a sinusoid like this, you are averaging over this part of the cycle. Okay, if it is not intuitive, then what I mean is, so this is TS by 4. I'm assuming n equal to 4, right? So if you have a sinusoid which has a frequency of TS, then it means that it goes maximum here, 0 here, then goes something like this, right? Right. So this is at omega s. If you have an input at 2 omega s, what would it look like? It will have a full cycle here, right? So which means it's going to have something. Correct? And then this. So which means that you are averaging over half cycle, right? So which means that for this particular case, you are going to get non-zero. right? For a sinusoid, you are going to get non-zero. For a cosinusoid, you are going to get a 0. But if you add up sinusoid plus cosinusoid j, you are going to get a non-zero, right? So you're going to get non-zero. So the key thing is that this is going to be non-zero, right? So if this is non-zero and you multiply by s of t, obviously you are going to get non-zero, right? So this does not naturally imply it's band pass filtering, right? So what this is saying is that this very action of switching is creating tones, sidebands, and those tones are, if they are close by, then the bandpass filter the lousy bandpass filter that I'm saying should follow should also have higher roll off than if the tones were not there, right? So this only does that job. It does not anywhere say till now. It does not say that if there is an input at 2 omega s, it is going to get filtered. That's an important distinction to make. Because at that time, you will have to see what is the harmonic response of h of 2 omega s. Right? Right now, we are only doing with h of omega s. Okay. Okay. So if time permits later on, I'll show you some architectures where this can be modified to get actual bandpass filter as you're asking, that 2 omega s can also be filtered out. So I'm not sure whether we have time or not, but if we have time, I'll show one. Any questions so far? Yes.
What is the motivation behind like tapping out the response at the node before s of t?
I can tap out from anywhere. So the thing is, this relationship is independent of wherever you're tapping out from, right? So
It can be at the output.
it can be at the output of the capacitor, but at the output of the capacitor, you only have DC, right? So yeah, at the output of the capacitor also, you are going to get some benefit, but if you have to see its full effect, it's better to see at places where you have, non-DC terms also.
Just for like taking out the complete effort.
Yeah, this is just an example, but this principle is general, right? So the reason, okay, so now let's come to what are the benefits of taking it out like this, other than the fact that the tones nearby tones you can get rid of, is that this entire thing, even though it looks complicated, can be made much simpler if you just recognize the fact that all the clocks of each of these kernels are non-overlapping, which essentially means that if kernel 1 is on, if the top kernel is on, the second kernel is off, and so on, right? There is no overlap between them, correct? Which means that the current either goes through this, or goes through this, or goes through this. It does not go simultaneously through any two at a time, right? It goes one at a time. If that is the case, then it essentially means, so now when I'm adding up, what am I doing? So if I add, let me redraw. So let me redraw and show you only two cases. So this is s of t. What does the signal here look like? It will look like when s of t is high, I'm going to get something, then it goes to 0, and then something goes to 0, and so on. Correct? The next guy is t minus ts by n. What does it look like? The same guy, it will be shifted. When I'm adding them up, what am I essentially doing? All these time shifted versions will stack up next to each other. Correct? So this is equivalent to saying that I have a single RC Okay, so let me take one step at a time. So it is equivalent to saying I have this guy, and so on, and they are connected together. And I am interested in sorry. Does it make sense? Because in one path, in one phase, you are having this discharging, another phase you are having discharging. And these two phases are not interacting with each other anyhow, because there is no overlap between the clocks. Correct? So similarly, I can have, if it, because I have n phases, what we are doing is we can have n of them together. So this is st minus ts by n, and this is st minus n minus 1 by n, right? And now what will this node voltage look like? This node voltage will essentially, for the on time of this will look like, let me now color code maybe. So this, for the second phase, when this is on, it will look like this. And when the third phase comes, I mean, it will probably look like this, and so on. So you are stacking them up just like you are doing, here. Right? So this is, even though the block diagram seemed complicated, in a principle, if you think about it, it's an extremely simple circuit. You have 1 R, 4 switches, 4 capacitors. Right? And because you have n phases and each phase has a path associated with it, these are called n-path circuits. And this does filtering, so hence it's called an n-path filter. Right? So if you search the literature over the last 10 years, you are going to see that there's a whole bunch of papers which has come out on n-path filters, and an extremely useful circuit, an extremely powerful circuit which can do many things which are seemingly much difficult in an LTI, using an LTI network. Okay. Any questions so far? Okay. So maybe in the last 10 minutes that we have, what maybe I can do is try to show you something weird thing that happens in an LPTV network, which we have to be cognizant about, which is different from an which is different from an LTI network. What I mean is something that happens in LPTV network, which is different from an LTI network. And that is with regards to the impedance and admittance. So so by the way, I'm going into a slightly different discussion related to LPDB. If you have any questions, whatever we have discussed till now, can bring it up right now. Okay. So obviously one of the applications is bandpass filtering, because if you are okay with, let's say, even if we stop the LTI, I mean, evolving the circuit from this, right? This is, let's say, is your circuit, nothing else to be done. Then also you see that if you have an input at omega s, you are going to get an output. If you have input slightly away from omega s, not at 2 omega s, but slightly away from 2 omega s, you are going to get attenuation. Correct? So, and the Q factor of that is how much? Right? So you can, so basically you are seeing this, right? I am ignoring the other stuff here. So here, I'm ignoring the other stuff here. This is omega s. So what is this bandwidth? this one-sided bandwidth is 1 by, I mean, yeah, I mean, one-sided bandwidth is NRC, correct? Two-sided is 2 NRC, right? So your two-sided is 2 NRC. So your Q factor is?
It would be 1 by NRC.
Sorry.
Okay.
Correct. Yeah, correct. So your, this thing was 1 plus J omega NRC, right? Right. So in terms of, if I write it in terms of 3 dB, so 1 plus 2 J 2 pi F times NRC. So your F 3 dB is 1 by 2 pi NRC, right? This is for the low pass. For the band pass, it becomes twice of that because you have both sided. So this becomes 1 by pi NRC, correct? And your Q factor, if I go by the definition of center frequency by bandwidth, so this is Fs by 1 by pi NRC, which is pi NRC Fs. Correct? So now application of this. So to understand the application of this, let's compare with any LTI bandpass filter, right? So what is the simplest LTI bandpass filter?
The first.
Yeah, I mean, bandpass filter you can assume to be this, right? Second order, right? You can only have second order roll-off. Second order roll-off will, and I think we talked about this. The Q factor of this is fixed, right? The Q factor of this is fixed, and it's if you have certain amount of R, L, and C, right? So your Q factor is essentially dependent on L and C and R, right? And the value of the problem with that is your L is also lossy in a chip, and that loss is very difficult to control, which means that just because I am writing an L here like this, it does not mean that I can get a pristine L. The L comes with R, and you can assume that R has been incorporated here, right? So which means that given an L and an R, a second order bandpass filter will have a finite Q beyond which you cannot go. Okay, but now see the Q factor of this N-path filter. Pi is constant and Fs is user controllable, right? Now, point number 1 is this guy is not electronically programmable. You fix L, you fix C, your center frequency is fixed. You cannot do anything unless you go and have switches and you change L's and C's, and that will have add its own losses, right? In this case, it is electronically programmable. You just have to do, all you have to do is change the clocking frequency. The position of the peaks are going to change, right? Number 1. Number 2, Q factor, user controllable. If you want, you can have more number of phases. You can have higher N, or you can have higher R, or you can have higher C. Yeah, you can keep increasing them. You can get sharper and sharper roll-off. Another thing which is not apparent from here is given an RLC in a LTI network, the bandwidth is also directly proportional to the center frequency, right? You can do it yourself, maybe DIY, do it yourself. That find out the ratio of F0 over the 3 dB frequency for the RLC network. So you'll see that it is independent of F0, which essentially means that if you increase F0, your bandwidth increases, which might be good, might not be good. But for a bandpass filtering application, that's not good, because I want sharp, narrow bandpass filtering at any frequency of interest. But just because I move the center frequency by bandwidth increases, that's not good, right? But in our case, where we have a frequency translated effects, essentially what did we do? We created a low pass filter at a small frequency and we upconverted its response to bandpass. And that, because of that, your bandwidth is not dependent on the center frequency. Because the bandwidth is not dependent on the center frequency, if I keep on increasing the center frequency, your Q factor increases. Right? So which is a good thing in this particular, if in a narrowband sharp bandpass filtering. Right? So these are the main applications of in-pass filters, where it kind of trumps the LTI equivalence. Okay.
We cannot like go very high with the frequency system.
Yeah, that's a problem, right? So his point is in application thing that and these RLC networks, because they are not dependent on clock, you do not have to give sharp clocks, high frequency clocks. So the problem with bandpass filter, these LPDB networks, is that it is dependent on some sort of clock. If you want these things to happen at higher frequencies, the clock has to be higher frequency, and that's the problem, and that's genuine problem. So these type of filters, that's why do not work very well at higher frequencies. When I say higher, I mean higher is dependent on technology, but typically few gigahertz is fine in modern technologies. If you want to go to tens of gigahertz, not a very good solution. Yeah, that's a practical aspect of it. Yeah, we'll be limited by clocking, right? You had a question.
We are using LTP PTV system in place of LTI system.
Correct.
Like for the bandpass.
Yes. Right. So this is one application of it. Okay. We're out of time. Any other question? Last question we can take. Okay, fine. Then we'll stop here.
The benefits are that we reduce